Now our topic today is on linear momentum, which is the opposite of what we did in our last video. In our last video, we did equilibrium of forces, that is condition under which the body will be in state of equilibrium as a result of balanced force. It may be as a result of downward forces equal to upward forces, or clockwise movement is equal to anti-clockwise movement, or if the force in a moving object is equal to frictional force. So the body will move with what? Uniform velocity, that it will not accelerate. But today's old, we are going to base it on what? On balanced force. That is, the body will accelerate as a result of unbalanced force. And we are going to use Newton's laws of motion. We are going to start from the first law. And the first Newton's laws of motion state that an object will remain in a state of rest or moving with uniform velocity unless it's acted upon by an external force. That is, if you have an object at a point like this, if you place object at a point, this object is supposed to remain here like this forever and ever. But if at the end of the day you now discover that I found object here, it means something has acted upon it. And what is that thing that can change the position of an object? It's as a result of force. So likewise, if an object is moving, that object is supposed to move with uniform speed. What will not change? What will increase the speed of the object or decrease the speed of object? It's as a result of force. So this law is totally related to what? The state, the weight of an object. That's why we call it law of inertia. They may ask you to state the law of inertia. It's still the same thing as Newton's first law. Because inertia itself is what? The tendency of body to remain at rest like this as a result of its weight. Or moving with what? Uniform speed. So if you are asked to state the law of inertia, it's the same thing as what? The Newton's first law. Now, let's go to Newton's second law that says the rate of change in momentum of an object is directly proportional to applied force, and it takes place in the direction of the force. Now, from that, we need to, let's break the content of the law down. The first thing is momentum. Momentum itself is product of mass and what? Its velocity. When we now say change in momentum, like you have it in what? Acceleration, change in velocity. Change in momentum means a final momentum minus initial momentum. What will be the final momentum? That is mv. Then what will now be the initial momentum? That is mu. Now we say change in momentum. It means mv minus mu. But when we say rate in physics, it means divided by time. That is per unit time. So this one means rate of change in momentum means mv minus mu over t. But the law says the rate of change in momentum, that is the whole of this one, very directly with what? Applied force. And it takes place in the direction of the force. Therefore, you can say this one very directly with force. But in mathematics, in variation, there's very direct variation. This is direct variation. If you have A vary with B, it's the same thing as B vary with what? A. Therefore, we are going to apply this one as the force very directly as the what? Rate of change in momentum. So we are going to have it like the force very directly with what? Rate of change in momentum. So we are going to use this law to get two things. The first one to prove that momentum is same thing as what? It has the same dimension as impulse. It's equal to impulse. And as well, we are going to use it to prove that force is equal to mass times acceleration. Now let's go. This one, like we normally do in mathematics, when you remove this one, you replace it with what? Equal to and constant. Therefore, force is equal to K open bracket mv minus mu over t. Now let's cross multiply. Therefore, we have ft, which is, this is impulse itself. because impulse is product of force and time taking. Therefore, this one equal to K, open bracket, mv minus mu. Now, dimensionally, impulse is equal to change in momentum. Because impulse, you see that, when we say change in momentum, we have the same dimension as momentum. That is just like change in velocity. We have the same unit as what? Dimension as what? Velocity itself. Therefore, let's try to see this one, whether you are going to get this or not. For here, we have Ft, which is equal to, let's change this one to mass times acceleration. That's formula for force. We have mass times acceleration, then times this t. Then let's break this one down. Acceleration itself, that is velocity over time, which is equal to m times v over t times this t. So this one cancels this. So automatically the Ft is equal to mv, which shows that impulse is equal to momentum. Now let's come back here. If impulse is equal to change in momentum or momentum, it means this one equal to this. Then what will now be the value of this k? Therefore, just go to where you have, just like when you have something like this, 2 times 5 is equal to k open bracket 5 plus 5. So if you have something like this, since this one will give you 10 and this one also will give you 10. So it shows that this k is automatically equal to what? 1. Since impulse is dimensionally equal to change in momentum, it means the value of k here is 1. So therefore, if k is equal to 1, it means this one become Ft is equal to mv minus mu. Therefore, impulse is equal to change in momentum. And don't forget, impulse, as you can see it, is equal to product of force and time during which it acts. While momentum is product of mass and is velocity. Product of mass and is velocity. So we prove this, that is impulse is equal to momentum. Let's go and prove that force itself is equal to mass and acceleration. So we are going to continue from here. So from this same equation, we now divide both sides by t. Therefore, we are going to have F is equal to mv minus mu over t. Therefore, F is equal to factor m out, m open bracket v minus u over t. And the whole of this one is formula for acceleration. Don't forget, acceleration is what? Change in velocity over time. So this one is a. So automatically our F is equal to ma. Therefore, from second law of motion, we can prove that impulse is equal to change in momentum or momentum itself, and force is equal to mass times acceleration. Now let's go to the third law. The third law states that the action and reaction are equal and opposite. Action and reaction are equal and opposite. Therefore, if you use, that's why most of the time, if you use your thumb to press the thumb pin on the board, you feel what? Pain. So which means as you are supplying force to press the pin also is supplying what? The same amount of force to your thumb. Therefore, the action is your own force, the reaction is one from the top of the pin. Therefore, when you have an object like this, if you tie an object with what? Rope, like this, and you are holding it here. So the weight of this object itself will be acting downward. Then the tension in the rope will be acting upward. If both of them are equal, the object will what? Will be in state of what? Equilibrium, and it will be static, it will not move. Therefore, the action is the weight, which is equal to mg. The reaction is this one that is acting upward. Therefore, the action and the reaction, they are equal, but they are acting in opposite direction. You can see the law is just explaining the real life experience. Now, if the object is now moving, so it means either the action, the weight, is greater than the tension, or the tension is greater than the what? the weight. Object will move down if the weight, that is, it will move down if the weight is greater than the tension. But it will move upward if the tension is greater than the what? Than the weight. So in that case, for the object to move upward, for this to move upward with this arrangement, it means tension minus weight, that is mg, is equal to ma. But for it to move down, it means the weight mg minus tension is equal to ma. And that is that about what? Applications of Newton laws of motion. So the next topic will be based on what? Collision, which is also part of linear momentum. Don't forget, when we say linear momentum, there's a reason why we call it linear momentum. We still have angular momentum. This one means unbalanced force acting on an object that is moving on a straight line.